Today we're going to look at some more alkanes and things called isomers. So maybe you want to look up what an isomer is, but we can do that later. So let's start with the last alkane we had yesterday. What was the name of the last alkane? Butane. Pentane.
Yes.
All right, we'll start with the second last one then. Butane. Okay. So butane has 4 carbons. If I use the general formula CnH2n plus 2, this is something I must remember. It's a have to, because that identifies the alkanes. Okay, so but 4 carbons, so C4H. Come babies. 10. C4H10. Now, this straight chain butane looks like this. The structural formula has 4 carbons in a row. Actually, this thing, we draw it as a straight chain, but I'll show you what it actually looks like. Can you remember from last year what the geometry is of a carbon-based molecule like methane? What is the shape of methane? Trigonal planar right here. Anything else? Tetrahedral right here. Anything else? No idea I hear. Anything else? Is it not tetrahedral?
Yes, because 10. You never 10. That's my logic.
So in reality, this molecule of butane will look like something like this. Can you see? Just need to get another one off here with my stupid hand. It's getting better. Yesterday I could change the gears with it. Okay? So my car is automatic, but you still need to be able to flip the lever. So it's getting stronger. It's really, I'm very happy about that. Okay, so there. So this thing isn't really straight, but I call it straight. Okay, so I'm going to introduce you to something else now that works actually better when the molecules becomes very long. It's called the skeleton structure. The skeleton structure just uses lines, and at the tip of a line there's a carbon with its hydrogens. So here's a carbon, this is the first carbon with its 3 hydrogens. There will be a carbon with its 2 hydrogens. Then the line makes a zigzag. There is the next carbon with its 2 hydrogens. There is the next carbon with its 2 hydrogens. So this is 1, 2, 3, 4 carbons. You see that? So technically, we should be drawing this thing out like this. To actually get the real picture of what it looks like.
I'm sorry, ma'am. Why are we doing it like that? Because it's a tetrahedral?
Yes, because it's kind of tetrahedral. The bonds are they are spaced as far as possible from each other. So if you build a model of it, you get the idea of the three-dimensional nature. Because all the atoms are lying in the same plane like this, all the carbon atoms, they call it a straight chain, but it's not really straight. Are you with me now?
Yes.
Okay. So this is the structural formula. They don't really test the skeleton formula, but if you go into chemistry and biology, because the molecules are macromolecules, they don't put all the symbols of the elements in there. They use a skeleton structure.
So they don't draw that?
They draw something like this, but this one is now for a simple molecule like butane. Okay. Good.
Can we copy that?
You want to copy this? All right. Because we've got it, I just want to move on from it. We've already got the butane, you just don't have the skeleton structure. And you've got the condensed molecular formula as well. Okay. So now, I'm going to play devil's advocate. Who says that the atoms combine like this to form butane? Who says that the atoms must all be carbon to carbon to carbon to carbon? Can't it perhaps be like this? And here comes the fun in this chemistry. Sorry, I can't put this on the video now because I realized if I change from this to visualizer, the thing doesn't record the whiteboard, so I can't. Who says it doesn't look like this? Does it still have 4 carbons in it?
Yes.
Does it still have 10 hydrogens in it?
Yes.
Okay. But this molecule is a shorter, more round molecule than that one where the carbon atoms were all joined from one to the next, to the next, to the next. So the properties of this molecule will be different. Its boiling point will be different to that other one. Because the moment the molecule has a smaller surface or a shorter chain, the van der Waals forces between it changes. So the boiling point, the intermolecular forces changes. So the boiling points will be different. So that is why we have to have a way to distinguish the difference between this molecule and that long chain carbon, hydrocarbon. It's still an hydrocarbon, it's still a saturated hydrocarbon, but now one of the carbon atoms formed a side chain. It's not part of the longest chain in the molecule anymore. Now this is an isomer of butane. So I'm going to draw it here. It's still C4H10. But now one of these carbon atoms has moved to the second carbon in the chain, the middle carbon of the chain. So now the molecule will have different physical properties because the intermolecular forces will change. And we know that it's van der Waals forces, or London forces in this case. Why would the intermolecular forces be London forces? Let's look at it. Okay? How did we determine the nature of the bond? Electrostatics? Electronegativities. Where will you find the electronegativities of the elements? So what is the nature of the CH bond? Carbon is 2.5 and hydrogen is 2.1. So there is a polarity to the bond, and the hydrogens will all be polarized positively. Okay? So the charge distribution, I'm taking you a year back now. Are you fine with that?
Yes.
The charge distribution on this molecule will be symmetrical. All around the carbon atoms, the hydrogens stick out like little positively polarized things. And this one the same. The polarization here is 0. They are non-polar molecules. They are all non-polar molecules. Both these molecules are non-polar because the charge distribution is symmetrical. The molecules are non-polar. They are non-polar, so it means that the intermolecular force, please don't you use that to answer a question. IMF is my lazy way of doing it. Intermolecular forces would be London forces. Some people prefer induced dipole forces. Some people prefer momentarily dipole forces. Doesn't matter, I understand all that is in my frame of reference London forces. Okay. So who will have the stronger London forces here? The one with the longest chain will have the stronger London forces. So this molecule will have the stronger intermolecular forces, so it will have the highest boiling point and melting point as well, for that matter. This molecule is more round, so the London forces will be weaker. Yes.
So, ma'am, is this based for all of the organic compounds that they change from the long molecule to the isomer, they will change into London forces?
Well, methane can't, ethane can't, and propane can't. So butane is the first one that will do something like that. Right.
So,
With the very short chains like methane, ethane, and propane, it can't. So butane is the first one that can form an isomer. Yeah.
So now, this molecule, the first one, is the has stronger intermolecular force because it has the longer chain, so
yes.
therefore it has the highest boiling point.
You see, it's got a bigger surface area. That's why there's more space for the molecules to make contact, to lie next to each other. So the London forces will be stronger. When you have something that is more or less round, they can touch there, and they can touch there, but then this part will be left untouched. So it's a smaller area that they can have contact with one another, so a weaker London force. Okay. So the boiling points will be lower, the melting points will be lower. Yeah? I am recording, so I'll put it on, but you're welcome to. Yes.
So for the skeleton structure, right, on yours, you have one line. But in the textbook, there's like a line underneath.
That's for double bonds. I'm still getting there. Okay, I want to first just ease you into the new chemistry. Okay. Can I take this nature of the bonds away now?
Yes, we can.
Okay. So they had to get a method of naming this isomer so that they know exactly which molecule of butane it is. Okay? It's called the IUPAC naming rules or rules. So it stands for International Unit of Pure and Applied Chemistry. I don't know. Your textbook will give you that information. Okay? So what is the name of this molecule? That's got 4 carbons, 10 hydrogens, but it's not a straight chain molecule.
Oh, the isomer.
Yeah, the isomer. Okay. Now this isomer is called a chain isomer because the chain has changed in length. So it's a chain isomer of butane. Okay. Now, the rules are, you find the longest carbon chain in that molecule and you number the carbon atoms in the chain. So here, because it's a habit, I'll start from the left-hand side. 1, 2, 3. The longest continuous carbon chain in this molecule is 3. You agree? Okay. But look now what I'm going to do to the model. You see the 3 there. But the 3 could be there as well. Or the 3 could be there as well. It doesn't matter. I could say that this is number 3. I don't have to count straight. I can also count around corners. Alright. Good. So, but I'll keep it straight. Because it doesn't matter whether I go straight across, whether I go down around the corner. I won't find anything longer than 3 consecutive carbons in the chain. I can even start from the right. 1, 2, 3. It doesn't matter. I'll only get 3. I can start from this side. 1, 2, 3. Doesn't matter. Alright? So, initially you need to play with these to see what is the longest chain. Yes?
So like
because the fourth is on the second.
It's not bonded with the other one.
Yes, it's not here anymore. You see there in the original molecule, they all formed a continuous chain where the 4 carbon atoms were joined from one to the next to the next to the next. Here it's from one to the next to the next, and you have to stop and you have to go somewhere in the middle. Okay. So the name of this thing, the base name, will be determined by the carbon, the chain with 3 carbons in it. So that is propane. You agree? Prop means 3. So this is a propane. And this thing that forms the side chain, this is a side chain. Or a side, it's a functional group. What would it have been if it was on its own, by itself? It would have been methane. Okay? Are you with me? The C with the 4 hydrogens would have been methane. Yes?
Is there a link to the carbon?
Yes, I'm getting there. I'm trying to explain something. Because one of the hydrogens are gone from the methane, and this methane is a side chain, it changes to methyl. So this is methyl propane. Because that single carbon is joined to the longer chain. It comes from methane, the idea of methane, but now it's a side chain, so it's methyl. Technically, joined to this methyl must be the number to which, the number of the carbon atom to which it has joined. So it is 2-methyl propane. But the 2 in this example is irrelevant because it can't join to the third one and it can't join to the first one, because if it joins to the third or the first one, it is the original structure of the molecule. It's butane. While we're waiting for Nalo to build that molecule, what is the condensed structural formula for pentane? CH3, CH2, 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 CH3, the longer one. Okay. So Nalo has changed the molecule now. Okay, so there it is. She has changed the molecule. She took one of the carbons in from that long chain and she placed it here on the second carbon. You agree that the chain is now shorter, and this part of it will be more like it's rounder, because of the orientation of the atoms in the bonds. we don't get an idea of what the molecule looks like when we draw it as a Cooper structure or a molecular structure. If I would use the condensed structural formula for this, look at what happens. The first carbon has 3 H's to it. The second carbon has 1 H to it. Can you see that? But then it's got a side chain with CH3. And then it's got CH2, and then it's got another CH3. Now you will understand why I didn't want to put this down first. When you suggested I put it down, I didn't deliberately, because look at the difference between this condensed formula and this condensed formula. What is the difference? This is not a side chain. This refers to these 3 CH2 atoms. Can you see that?
Yes, ma'am.
But in here, this part is this part. That is a side chain, a functional group. So I'm scared that you will confuse these two. Yes, I did try. If the brackets has a CH2 in it, it refers to these CH2. They are not side chains. They are part of the molecule, part of the long chain. But the moment the group of atoms in the brackets has a CH3 in them, that moment it's a side chain, the methyl group.
Does it matter when you put the CH3?
The CH3 will come after the carbon to which it was bonded. So you can't put the CH3 before the CH. You can't put this there, because then it means that this atom have more than 4 bonds. So the CH3 in the brackets as the functional group, the side chain, is written after the carbon to which it is joined. Okay. We need to name this compound now. Any suggestions?
Is it 2-methyl butane?
Yes. So we number the carbon atom 1, 2, 3, 4.
Ma'am, I don't get the 2 part. Why?
The methyl group is joined to the second carbon in the chain.
Can you join to any?
Let's see, can it join to the first one?
Yes, ma'am.
But then it's the pentane, the original molecule again. Can it join to the last one?
Yeah, I can.
Yes, it can, but then it's the straight chain molecule again, the original one. So it can't join to the first, and it can't join to the last carbon.
Only the second carbon.
Or the third carbon.
Okay, so I can say 3-methyl.
Wait,
butane.
let's see. Let's just see before we jump to conclusions. C, 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 C with this C there. because that's the next rule now. You have to count the longest chain carbons, you have to count them so that the side chain will be on the lowest numbered carbon. So if that methyl is on the third carbon, then what they do is they count from this side. 1, 2, 3, 4. You got me?
Yes, ma'am. The methyl always next to the 1.
No.
So can it be a 3, for example?
But in this molecule, if it's on the 3 in this molecule,
In a hexane,
it's going to be 2 again.
then it'll be 2.
Yes. We'll get to the next one, then you'll see your answer. The answer to your question is yes, it can be on the third, but not on this molecule, because this long chain is too short. So yes, it can be on 3, but not for pentane. The moment you put it on 3 for pentane, you just count the number of carbon atoms from the other side, from the other end. So both these molecules would be 2 dash methyl butane. Between a number and a letter comes a dash.
There is no dash in between.
No, all that should be one word. 2-methyl butane.
Wait, sorry, I'm so sorry. I'm
No
not-
problem.
Um,
That's fine.
Where are the two methyl? Can you like show me?
There is the methyl, and it's joined to the second carbon in the longest chain.
Oh, see,
So here is the methyl, and we wanted to say this is the third carbon, you see? But it's not, it's actually the second carbon. Okay, let me show you. The first molecule there is when you look at the methyl, at the compound from that side. Okay? But now, does the compound change when you turn the molecule around? No. So you understand now why the methyl is on the second carbon only. The moment you change it to that carbon, you actually have the same molecule. You're just looking at it from the other side. Yes.
So when you're counting, like to say 2, you count from where it's the closest to the...
Yes, you count from so that the methyl group will be on the lowest numbered carbon. The base chain is the longest chain in the molecule. And our base chain here has 4 carbons. There is another isomer. Yes. Let me show you. I'm just going to redraw this one and then I'll show you. So that is 2-methyl butane. Can I ask somebody to take the model and to make the chain shorter?
Oh, again. Wait,
Get help. Ask for advice.
Advice?
So the chain must be shorter, so how many carbons must be in the chain? 3.
This one. This one. Yeah. Oh yeah. No, in the middle. Remove the white one in the middle.
Yes, the tool, if you want to use, move those little things.
Like this. And then shove the white
But
one
you
in
can't
the
take
back.
atoms away, so you have to put these atoms where they...
This one. And then the bottom. Which bullet? Oh, this one.
Beautiful. See how round the molecule is now? Okay, so we kept that methyl group there, but we took one carbon from the chain of 4 carbons and we joined it there. Is it still something with 5 carbons and 12 hydrogens? Does it still have 12 hydrogens? Okay, so this is another chain isomer of pentane, but I can't call it pentane. Okay, I can't call it pentane because it's got different properties to pentane. It will have, of the 3 isomers of butane, of pentane, this will have the weakest London forces between the molecules. So, the boiling point will be the lowest. Okay. How will I get the name? What we do is we need to find the longest continuous chain. Now, just to be funny, I'm going to count from the top to the bottom. Because I want to show you that you must not just think of counting from left to right or right to left. You can count around the corners as well. If I count 1, 2, 3, it's still 3 carbons. If I count 1, 2, 3, it's still 3 carbons. It doesn't matter to which part of the molecule I'm looking. This part or that part or that part, doesn't matter. The longest chain is 3. So this is 3 carbons would be propane. Okay. Now, joint to the propane, here is a what? Methyl. And here is another methyl. Right. Okay. This is dimethyl propane. And to be technically correct is 2, 2 dash dimethyl. Okay, in this molecule, because it's so short, it doesn't make sense to put 2, 2. But both the methyl groups are on the second carbon in the chain. So that's why it's 2, and between numbers we put a comma.
So wait.
The methyl on the left-hand side is on 2, and the methyl on the right-hand side is on 2. So for each methyl, you must put the number down.
So you say.
But you don't say 2-methyl, 2-methyl propane. You shorten it by saying 2, 2 dimethyl propane.
Do you have to say 2?
Yes, it's a safe way to go about it. Although there is no other option There is no other position possible for the methyl groups in this molecule. Now they want to go home without homework.
Ma'am, we have a principal.
All right, I'll accept.